This content is provided for educational and entertainment purposes only. The information regarding automotive mechanics, sound engineering, and vehicle performance constitutes a historical and technical overview and does not serve as professional mechanical, legal, or safety advice. The high decibel audio levels discussed and presented in this recording have the potential to cause permanent hearing impairment if monitored at excessive volumes. Viewers are advised to use caution and utilize hearing protection where appropriate. Furthermore, any discussion of vehicle modifications or high-performance driving refers to activities that should only be performed by trained professionals in controlled environments. Many exhaust modifications and noise level adjustments are subject to strict local, state, and federal regulations, including the Clean Air Act and various municipal noise ordinances. We do not endorse or encourage the violation of any traffic laws or environmental regulations. Viewers must conduct their own due diligence and consult with certified automotive technicians or legal professionals before attempting any vehicle alterations. The American V8 engine is currently facing an existential crisis that most enthusiasts are not prepared to handle. We are witnessing the final decade of the internal combustion roar, as it has been known for nearly a century. Within the next few years, the visceral chest-thumping vibration of a high-displacement American muscle car will be replaced by the sterile high-frequency hum of electric motors. This is not just a change in technology. It is a fundamental shift in the American sensory experience. Research into psychoacoustics suggests that the low-frequency rumble of a cross-plane V8 triggers a specific physiological response in the human brain, releasing dopamine and cortisol in a way that modern synthetic sounds simply cannot replicate. For decades, Detroit was not just selling horsepower. They were selling a specific frequency. When you hear a 1969 Dodge Charger R/T idling at a stoplight, you aren't just hearing an engine. You are hearing a complex sequence of controlled explosions timed to a specific firing order that mimics the cadence of a human heartbeat under duress. This video is the definitive masterclass on that sound. We are going beyond the surface to analyze why these machines sound the way they do, the physics of the exhaust pulse, and the historical trends that led to the creation of the most iconic automotive soundtracks in history. If you have ever wondered why a Ford Mustang sounds inherently different from a Chevrolet Camaro, or why a Hemi engine has a mechanical thump that no other architecture can match, you are in the right place. By the end of this deep dive, you will possess a professional-grade understanding of automotive acoustics, allowing you to identify legendary engines by their decibel signature alone. The primary problem we are solving today for the American audience is the loss of automotive literacy in an era of digital isolation. As vehicles become more insulated and engines become smaller and turbocharged, the average enthusiast is losing the ability to distinguish between genuine mechanical prowess and synthesized engine notes pumped through cabin speakers. This masterclass restores that connection. We are diving into the step-by-step technical breakdown of the American sound to provide you with the tools to appreciate, preserve, and understand the engineering marvels that define the 20th century. We will examine historical trends in manifold design and the physics of backpressure to explain how a simple piece of bent steel tubing can transform a chaotic explosion into a symphony of power. To understand the roar of America, we must first analyze the foundational architecture of the American V8 engine, specifically the cross-plane crankshaft. Unlike European supercars that often utilize a flat-plane crank, resulting in a high-pitched Ferrari-like scream, the American muscle car relies on the cross-plane design. This configuration places the crank pins at 90-degree intervals. The result is an uneven firing order between the left and right cylinder banks. In a typical small-block Chevy, for instance, two cylinders on the same bank will fire in succession. This creates a massive pressure wave in the exhaust manifold that isn't immediately followed by a corresponding wave on the opposite side. This chugging or galloping effect is the technical basis for the muscle car rumble. It is a series of overlapping acoustic pulses that create a low-frequency interference pattern. When we look at data from acoustic mapping of a 1960s-era muscle car, we see high energy concentrations in the 40 to 100 Hz range. This is the sub-bass of the automotive world. It is a frequency you feel in your sternum before you hear it in your ears. Case studies of the 1968 Ford Mustang GT Fastback, used in the film Bullet, reveal just how much effort goes into capturing this specific sound. The audio engineers for that film didn't just record the car driving. They placed microphones in the engine bay, near the headers, and directly behind the tailpipes to capture the full spectrum of the 390 cubic inch V8. They found that the magic of the sound happened during deceleration. The burble and pop, caused by unburnt fuel igniting in the hot exhaust system. This is known as overrun, and it is a hallmark of high-performance tuning. It signifies an engine that is breathing so deeply and fueled so aggressively that it cannot fully contain its energy within the combustion chamber. This specific historical trend in sound design set the standard for every car movie that followed, establishing the V8 roar as the universal cinematic shorthand for power and rebellion. Furthermore, we must discuss the role of displacement and its direct correlation to acoustic volume. A larger cylinder volume moves a larger mass of air. When a 426 Hemi opens its exhaust valves, it is venting a massive volume of high-pressure gas into the headers. The Hemi name itself refers to the hemispherical combustion chamber, which allows for larger valves and a more direct flow path. From a sound design perspective, this results in a sharper attack on the initial sound wave. If you compare the idle of a 426 Hemi to a contemporary 289 small block Ford, the Hemi has a much more violent, percussive sound. The 289, being smaller and often revving higher, has a smoother, more rhythmic tone. These nuances are not accidental. They are the result of specific engineering choices made to maximize airflow, where the sound is a secondary, albeit legendary, byproduct. To truly master this topic, one must also understand the evolution of the exhaust system itself. In the early days of the muscle car era, many vehicles utilized glass-packed mufflers. These were essentially straight pipes wrapped in fiberglass insulation. They provided very little sound dampening, allowing the raw mechanical noise of the engine to reach the atmosphere virtually unfiltered. As we progressed into the 1970s and 80s, chambered mufflers became the industry standard. These used internal baffles to bounce sound waves against each other, using destructive interference to cancel out certain frequencies while amplifying others. This is why a modern Dodge Challenger Hellcat can sound both refined at a cruise and absolutely terrifying at wide-open throttle. The engineers have used the physics of sound to create a dual-personality vehicle. They have mapped the resonance of the cabin to ensure that the drone, the annoying constant hum at highway speeds, is eliminated, while the scream at 6,000 revolutions per minute is highlighted. We also have to consider the impact of header design. Long tube headers versus shorty headers change the sound profile significantly. Long tube headers allow the exhaust pulses from each cylinder to travel further before merging, which helps in scavenging, using the vacuum created by one pulse to pull the next pulse out of the cylinder. Acoustically, long tube headers produce a deeper, more resonant tone with more distinct individual pulses. Shorty headers, often used in tighter engine bays, tend to result in a higher-pitched, more raspy sound because the pulses merge much sooner, creating more turbulence and high-frequency noise. This is a critical distinction for anyone looking to understand the potential outcomes of different mechanical setups. Historical trends show that the most sought-after vintage sounds almost always come from vehicles with long tube headers and large-diameter dual exhaust systems with an H-pipe or X-pipe. The H-pipe and X-pipe are two components that define the voice of a muscle car. An H-pipe connects the two exhaust banks with a straight crossover tube. This balances the pressure between the banks and emphasizes the low-end torque and the traditional thumping sound. The X-pipe, where the two banks cross over in an X shape, allows for more efficient flow at high RPMs and creates a higher-pitched, more exotic or nasal tone. This is a perfect example of how small changes in plumbing can fundamentally alter the identity of a vehicle. A Ford Mustang with an H-pipe sounds like a classic 1960s cruiser. The same car with an X-pipe sounds like a modern Trans Am race car. As we progress through this 10-part masterclass, we will continue to strip away the layers of these legendary machines. We are not just looking at cars as transport, we are looking at them as acoustic instruments. The Roar of America is a complex tapestry of mechanical engineering, physics, and cultural history. By studying the specific firing orders, the metallurgy of the manifolds, and the psychoacoustic impact of these frequencies, we gain a deeper appreciation for an era of engineering that may never be repeated. We are documenting the soul of the machine before the silence takes over. Stay tuned as we move into the specific profiles of the Big Three and dissect the individual signatures that have echoed across American highways for over 70 years. To understand the sonic fingerprints of the Big Three, we must begin with the Ford Motor Company and the specific mechanical geometry that defines the blue oval sound. Imagine it is the summer of 2026, and a young enthusiast named Jackson is standing in a garage in suburban Ohio. He is looking at a pristine 1969 Mustang Boss 302. In this future, where the silent hum of high-voltage battery packs dominates the suburban landscape, The act of turning the key on a high-compression Windsor engine is a deliberate choice to engage with the dying acoustic art form. When Jackson engages the starter, the sound that erupts is not just noise. It is a calculated result of the 154263778 firing order common to the early small-block Fords. This specific sequence dictates how the pressure waves interact within the exhaust manifolds. In a Ford small block, the pulses are spaced in a way that creates a tighter, more rhythmic cadence that many sound engineers describe as tearing silk. Historical trends in automotive acoustics show that Ford engines, particularly those with the 289 and 302 cubic inch displacements, possess a higher frequency resonance compared to their counterparts from Detroit. This is largely due to the shorter stroke of these engines, which allows them to reach higher revolutions per minute more quickly. The sound waves produced at 6,000 revolutions per minute in a Boss 302 are closer together in the time domain, creating a continuous high-pitched wail that is fundamentally different from the low-frequency thud of a heavy-duty truck engine. Step by step, we can analyze how the Ford sound changes as the engine architecture evolves. If Jackson were to swap that 302 for a 351 Windsor, the firing order changes to 137-26548. This change is subtle but profound. By shifting the sequence, Ford engineers altered the internal balance and the way exhaust gases scavenge from the cylinders. The 351 Windsor has a more aggressive, syncopated growl. It sounds heavier, more deliberate. This is because the larger stroke and different firing sequence create a distinct acoustic overlap. In our 2026 case study, Jackson uses a spectrum analyzer on his tablet to visualize the sound. He notices that the 351 produces more energy in the 120 to 150 Hz range, which provides that signature mid-range punch that Ford fans recognize instantly. This is the sound of a mechanical system operating at peak volumetric efficiency, where the exhaust notes are not just the byproduct, but a rhythmic confirmation of the engine's breathing capability. Shifting our focus to General Motors, we encounter the small block Chevy, or SBC. This engine architecture is perhaps the most documented mechanical sound in history. For decades, the 1843657 firing order of the 350 Chevy V8 has been the heartbeat of the American hot rod. Unlike the Ford, the Chevy sound is often described as a sewing machine on steroids. It is remarkably consistent and balanced. This balance comes from the symmetry of the engine block and the intake manifold design. When we look at historical trends from the peak muscle car era of 1967 to 1971, the Chevy 350 and the larger 396 and 454 big blocks produced a sound that was rounder and more mellow. Imagine if you are standing at a drag strip in 2026, watching a vintage Chevelle SS 454 staging at the line. As the driver holds the car against the brake, the idle is a deep rhythmic lope. This lope is caused by a high-lift camshaft that creates a momentary overlap where both the intake and exhaust valves are open at the same time. This allows a small amount of exhaust gas to escape back into the intake and unburnt fuel to enter the exhaust, resulting in that iconic irregular popping sound. The potential outcomes of this setup are a terrifyingly powerful acoustic presence that signals massive torque even before the car moves an inch. The evolution of the GM sound reached a turning point with the introduction of the LS engine family in the late 1990s. While the firing order remained the same as the classic SBC, the change in cylinder head design and the shift to aluminum blocks altered the timbre of the engine. Aluminum, being less dense than cast iron, does not dampen sound as effectively. This is why an LS3 in a modern Corvette or Camaro has a sharper, more mechanical clatter at idle compared to a 1970s small block. The sound is more industrial, more efficient. In our 2026 scenario, Jackson compares his Mustang to his friend Sarah's LS-swapped C10 truck. He notices that while his Ford has a melodic, almost musical quality, Sarah's Chevy has a raw percussive force that feels more modern and aggressive. This is a classic example of how material science directly influences the audio profile of a muscle car. The thickness of the cylinder walls and the density of the block act as a natural filter for the internal combustion events, and the historical trend toward lighter materials has gradually sharpened the American roar. Finally, we must address the most violent of the three signatures, the Mopar sound. Whether it is a 446-pack or the legendary 426 Hemi, Chrysler's engines have always occupied the loudest, most aggressive end of the spectrum. The Hemi engine, with its hemispherical combustion chambers, allows for massive valves and a straight-off-the-piston exhaust path. This means that the sound waves leaving a Hemi are less distorted by the twists and turns of a conventional cylinder head. When a Hemi fires, the sound is described by many as a physical hammer blow. Historical trends in top fuel drag racing, which utilize Hemi-based architecture, show that these engines produce sound pressure levels that can literally shake the earth. For the street-legal muscle cars of the 1960s and 70s, this translated into a deep guttural roar that was unmatched by Ford or Chevy. The 426 Hemi does not just rumble, it thumps. It has a mechanical density to its sound that suggests an incredible amount of internal mass, moving at high velocity. Step by step, the reason for this Mopar dominance in the low-frequency range is the sheer volume of air these engines can process. A 440 cubic inch big block moving at 5,000 revolutions per minute is displacing an enormous amount of atmosphere every second. The exhaust system has to fight to keep up, and that struggle creates back pressure which, when released, results in a massive acoustic explosion. In 2026, when these vehicles are seen as rolling museums, the sound of a Mopar cold start is enough to stop traffic. It is a violent, uncompromising noise that refuses to be muffled. The potential outcomes of hearing a Hemi at full throttle include a permanent recalibration of what you consider to be loud. We see this in case studies of 1970 Plymouth Hemi Cudas, where the factory exhaust was designed to be as free-flowing as possible within legal limits, resulting in a decibel level that pushed the boundaries of municipal noise ordinances of the time. As Jackson and Sarah compare their vehicles in the quiet of a 2026 afternoon, they realize they are listening to three different philosophies of power. The Ford is the precision instrument, the Chevy is the balanced workhorse, and the Mopar is the blunt force object. But these sounds are not just generated by the engines themselves. The way that sound travels from the cylinder through the headers, into the collectors, and out through the pipes is where the true alchemy happens. Every bend in the pipe, every weld in the muffler, and every inch of diameter change acts as a musical instrument, tuning the raw chaos of the engine into the roar of America. But what happens when the length of those pipes is changed by just a fraction of an inch? What occurs when the temperature of the exhaust gas drops as it reaches the tailpipe, changing the speed of sound itself? We are about to dive into the hidden physics of the exhaust pulse, and how the diameter of your tailpipe can completely transform the identity of your car. To understand the true physics of the exhaust pulse, we have to look at the exhaust system not as a series of pipes, but as a complex musical instrument designed to manage gas velocity and acoustic resonance. When an exhaust valve opens in a high-performance V8 engine, it releases a slug of high-pressure gas that travels down the primary tube of the header at nearly the speed of sound. This is known as a pressure wave. However, the speed of sound is not a constant. It is heavily dependent on the temperature of the medium it is traveling through. In the context of a 1970 Plymouth Superbird, the exhaust gases leaving the combustion chamber can exceed 1,200 degrees Fahrenheit. At these temperatures, sound travels significantly faster than it does in the cool 70-degree ambient air outside the car. This temperature gradient creates a fascinating acoustic phenomenon where the sound signature of the car literally changes as the engine reaches operating temperature. Imagine if Jackson, our 2026 enthusiast, uses a thermal imaging camera alongside his acoustic sensors to monitor his exhaust system during a cold start. Initially, the sound is sharp and metallic because the cooler air inside the pipes is denser, causing the sound waves to move slower and bounce more frequently against the pipe walls. As the 304 stainless steel headers heat up, the speed of sound within the system increases. The pulses begin to move more fluidly, and the sharp metallic clatter gives way to a smooth, deep resonant frequency. This is a primary example of how thermodynamic variables dictate the auditory potential outcomes of a mechanical setup. Historical trends in exhaust design show that manufacturers specifically tuned pipe lengths to capitalize on this speed of sound variable, ensuring that at peak RPM, the pressure waves would reach the end of the pipe at the exact moment needed to maximize performance and sound quality. A critical step-by-step technical process occurring inside these pipes is scavenging. As each high-pressure pulse moves through the pipe, it creates a vacuum, a low-pressure area, directly behind it. This is not just a secondary effect. It is the engine's way of breathing. If the exhaust system is tuned correctly, this low-pressure area reaches the exhaust valve just as it opens for the next cycle, literally sucking the spent gases out of the cylinder. From a sound perspective, this scavenging process is what gives a muscle car its crisp, defined bark. When scavenging is efficient, the individual pulses are distinct and sharp. If the exhaust pipe is too large in diameter, the velocity of the gas drops, the vacuum effect is lost, and the sound becomes muddy and hollow. Case studies in automotive acoustics often highlight the 2.5-inch versus 3-inch pipe debate. Many owners assume that a larger pipe will always result in a better sound, but the data suggests otherwise for most street-driven V8s. A 3-inch pipe on a relatively stock 350 Chevy small block often leads to a loss of exhaust gas velocity. The sound waves lose their focus, resulting in a boomy, low-quality drone that can be physically taxing for the driver. Conversely, a 2.5-inch system maintains high velocity, keeping the pressure waves tightly packed and resulting in a more aggressive, high-definition sound profile. In Jackson's 2026 garage, he observes this firsthand by switching from a generic 3-inch kit to a custom mandrel-bent 2.5-inch system. The decibel level might be slightly lower, but the tonal quality, the richness of the harmonics, is vastly improved. This is because the smaller diameter pipe acts as a better waveguide for the high-frequency mechanical noises of the valve train and the combustion event. The point where the 4 primary tubes of a header merge into one is called the collector, and this is where the acoustic identity of each engine bank is forged. The length and diameter of the collector act as a resonator. A long collector tends to emphasize lower frequencies, producing a deep boat-like throb. A short, stubby collector creates a higher-pitched, more frantic sound often associated with drag racing. This is why a pro stock car sounds like a Gatling gun, while a street-legal cruiser has a more rhythmic rolling thunder sound. The collector is essentially a mixing bowl for sound waves. When 4 different pulses from 4 different cylinders hit the collector in rapid succession, they create a complex interference pattern. If the timing is right, the waves reinforce each other, creating a massive singular punch of sound. If the timing is off, the waves can cancel each other out, leading to a flat, uninspiring exhaust note. We also have to analyze the material of the pipes themselves. In 2026, Jackson has access to various alloys, but the historical standard was aluminized steel. This material has a specific density that provides a decent balance of durability and sound dampening. However, many modern enthusiasts prefer stainless steel, which is harder and thinner. Stainless steel exhaust systems are known for having a brighter, more raspier sound profile. The sound waves reflect off the hard internal surfaces of stainless steel with less absorption than they would in a softer, cast-iron manifold. This is why a modern muscle car with stainless headers often has a more metallic, mechanical ring to its exhaust note. Imagine if Sarah, Jackson's friend with the LS Swap C10, chose titanium pipes. Titanium is incredibly light and stiff, and it produces a high-frequency resonance that can make a V8 sound almost like a high-revving European engine at upper RPMs. This highlights how material science offers different potential outcomes for the final acoustic product. Then there is the matter of the exit point. The location where the exhaust finally meets the atmosphere is the final stage of the instrument. Side pipes, famously found on the Shelby Cobra or the 1969 Corvette, offer a completely different experience than rear exit tailpipes. Because side pipes are much shorter, there is less distance for the sound waves to be dampened by the pipe walls. The driver and passenger are also physically closer to the exit point, meaning they hear the raw, unfiltered pulses before they have a chance to dissipate or reflect off the pavement. Rear exit tailpipes, which run the full length of the car, allow for more standing waves to develop. These standing waves are what create the deep bass-heavy resonance that muscle cars are known for. The longer the pipe, the more opportunity there is for low-frequency waves to resonate, similar to how a longer pipe on a church organ produces a deeper note. Furthermore, the shape of the exhaust tip itself acts as a megaphone. A flared, chrome tip can actually amplify certain frequencies, while a turned-down tip that points toward the ground uses the pavement as a reflection board. When sound waves hit the asphalt, they are bounced back up toward the chassis of the car, which can increase the perceived volume inside the cabin. This is why many classic hot rods use turndowns. It makes the car feel and sound more powerful to the occupants, even if the exterior decibel level remains within legal limits. In 2026, acoustic engineers use digital modeling to predict how these reflections will interact with different road surfaces, from smooth asphalt to porous concrete, as each surface has a different absorption coefficient that alters the car's sound. As we have seen, the journey from the exhaust valve to the tailpipe is a high-speed transit of physics, chemistry, and music. Every component, from the header primary to the diameter of the tip, plays a role in defining the roar of America. But even the most perfectly tuned exhaust system is only as good as the fuel that powers the explosion. We are about to look at the chemistry of combustion and how different fuel types and air-fuel ratios can change the very color of the sound. What happens to the roar when you switch from standard pump gas to high-octane racing fuel, or even the synthetic e-fuels of 2026? Does the sound actually get sharper? And can you hear the difference in flame front velocity through a set of Flowmaster mufflers? We are diving into the hidden link between fuel chemistry and automotive acoustics next. To understand why the roar of a muscle car changes when you swap pump gas for high-octane racing fuel, we have to look at the chemistry of the flame front velocity. Inside the combustion chamber of a high-compression V8 like the 427 big block Chevy, the air-fuel mixture does not simply explode. Instead, it undergoes a rapid but controlled burn. The speed at which this flame travels across the piston crown is the flame front velocity. In a historical context, using leaded high-octane fuel allowed engineers to increase the compression ratio and advance the ignition timing significantly. When you advance the timing, the spark plug fires earlier in the compression stroke. This means the peak pressure of the combustion event occurs closer to top dead center. Acoustically, this results in a much sharper and more immediate pressure wave hitting the exhaust valve the moment it opens. Imagine it is 2026, and Jackson is at a specialized heritage track day where only vintage internal combustion vehicles are allowed. He has just drained the standard 93-octane pump gas from his Boss 302 and replaced it with a specialized 2026 synthetic e-fuel, designed to mimic the properties of 110-octane racing gas. As he adjusts the distributor to advance the timing by 6 degrees, the change in the idle is instantaneous. The engine sound shifts from a somewhat soft, rounded thud to a metallic, crystalline snap. This happens because the higher octane allows for a more stable and rapid pressure rise without the risk of pre-ignition or knocking. When the exhaust valve opens, the gas exiting the cylinder is at a higher pressure than it was with the lower octane fuel. This higher pressure translates directly into a higher amplitude sound wave. In automotive acoustics, amplitude is volume, but it is also perceived as the punch or the hit of the exhaust note. The potential outcomes of this tuning change are a more aggressive, high-definition sound that carries further and cuts through ambient noise with more authority. Step by step, we can analyze the impact of the air-fuel ratio on the texture of the sound. A rich mixture, where there is more fuel than oxygen, tends to produce a deeper and slightly muffled sound. This is because the excess fuel droplets can actually act as a minor dampening agent within the combustion chamber and the exhaust manifold. Historical trends in muscle car tuning often favored a slightly rich mixture for cooling purposes, which contributed to that heavy, wet rumble associated with classic Mopars. On the other hand, a lean mixture, where fuel is scarce, creates a much hotter and more violent combustion event. The sound produced by a lean-running engine is often described as raspy or thin. In 2026, Sarah monitors the data from the wideband oxygen sensors in her LS Swap C10. She notices that as the engine leans out during a high-speed pull, the exhaust note gains a high-frequency scream that wasn't there before. This is the sound of high-velocity gases moving through the headers at extreme temperatures, causing the metal of the pipes to ring like a bell. Case studies in engine acoustics show that the most iconic muscle car sounds, those pops and crackles on deceleration, are purely a function of fuel chemistry and exhaust temperature. When the driver lifts off the throttle at high RPM, the engine is still spinning fast, but the throttle blades are closed. This creates a high vacuum that pulls a small amount of extra fuel into the cylinders that doesn't fully ignite. This unburnt fuel travels into the red-hot exhaust headers where it finally meets oxygen and ignites. This is the overrun. If the exhaust system uses a chambered muffler like a Flowmaster, these small explosions are amplified and reflected off the internal baffles. The Flowmaster design uses a series of V-shaped plates to deflect sound waves back into each other. When an overrun explosion happens, the baffles create a series of echoes that give the pop a hollow, metallic character. This is distinct from a straight-through glass-packed muffler, which would produce a more muffled, thumping pop. In the year 2026, the introduction of carbon-neutral synthetic fuels has added a new layer to this acoustic science. These fuels are often more chemically pure than traditional petroleum-based gasoline. They lack the heavy aromatics and sulfur compounds found in 20th-century fuels. Data from acoustic testing shows that these synthetic fuels can result in a slightly cleaner, more clinical exhaust note. There is less of the low-frequency grit that comes from the uneven burning of complex hydrocarbons. For a purist like Jackson, this means his 302 sounds more like a modern racing engine and less like a vintage street bruiser. However, by adjusting the latent heat of vaporization through fuel additives, 2026 chemists can actually alter the speed of sound within the exhaust system. Since the speed of sound is faster and hotter, Less dense gases. A fuel that burns hotter will technically result in a different resonant frequency for the entire exhaust system. Another critical factor is the stoichiometric ratio. For gasoline, this is 14.7 parts air to 1 part fuel. But for E85, which Sarah uses in her truck, the ratio is closer to 9.8 to 1. This means Sarah is moving a significantly higher volume of liquid fuel through her engine to achieve the same power. This extra mass of fuel, combined with the cooling effect of alcohol, changes the density of the exhaust gas. Denser gas carries sound waves differently. E85-powered muscle cars often have a unique, heavy-duty sound that is somewhat deeper than gasoline-powered cars of the same displacement. It is a subtle difference, but to the trained ear, the E85 roar has a certain thickness to it, a result of the increased mass flow through the exhaust valves. Imagine if you could look inside the exhaust manifold of a Hemi while it was running at 6,000 revolutions per minute on high-octane fuel. You would see a series of blue and orange flames licking at the primary tubes. The sound inside that manifold is not a single roar but a series of distinct deafening cracks. The reason we hear it as a roar from the back of the car is because the exhaust pipes act as a low-pass filter. They smooth out those sharp cracks into the rolling thunder we love. The higher the octane and the more efficient the fuel burn, the more energy there is available to be converted into these sound waves. This is why a car that is perfectly tuned always sounds better than one that is running poorly. Clean combustion creates a coherent sound wave with clear harmonics, whereas an engine with a misfire or poor fueling creates a chaotic, muddy noise that lacks the musicality of a true legendary muscle car. The potential outcomes of experimenting with these fuel types in 2026 include discovering entirely new acoustic profiles for classic engines. As we move away from traditional fossil fuels, the roar of America is evolving. It is becoming more precise, more intentional, but the fundamental physics remains the same. The fuel dictates the energy of the explosion, and that energy is the source of every decibel that exits the tailpipe. We have spent so much time focusing on the exit of the sound, the exhaust, that we have completely ignored the other half of the symphony. The engine is an air pump, and for every pulse of air pushed out the back, a massive gulp of air must be sucked in through the front. The intake roar is the hidden, often overlooked high-frequency counterpart to the exhaust space. But what happens when you remove the air cleaner and let a set of velocity stacks breathe directly from the atmosphere? What is the secret behind the whistling, sucking, and growling that happens under the hood before the exhaust even begins? We are moving from the back of the car to the front to analyze the terrifying sound of the intake next. Every high-performance engine is essentially a massive vacuum, and the intake sound is the audible evidence of that vacuum at work. While the exhaust is the violent release of energy, the intake is the aggressive, desperate inhale of the atmosphere. To understand the physics of the intake roar, we have to look at the fluid dynamics of air as it passes through a throttle body or a carburetor. Imagine it is a humid morning in 2026 in the high deserts of Arizona. A local builder named Marcus is tuning a Restomod 1970 Chevrolet Chevelle. He has opted for a classic naturally aspirated setup with a large diameter open element air cleaner. When Marcus snaps the throttle linkage from under the hood, there is a distinct sharp hiss followed by a deep hollow growl. This is the sound of air accelerating from a standstill to nearly 300 feet per second in a fraction of a heartbeat. The primary mechanical source of this sound in a vintage muscle car is the Venturi effect within the carburetor. As air is pulled through the narrowed neck of the carburetor barrels, its velocity increases while its pressure decreases. This pressure drop is what draws fuel out of the discharge nozzles, but it also creates a high-frequency whistling or rushing sound. Historical trends in automotive performance show that the transition from 2-barrel to 4-barrel carburetors wasn't just about horsepower. It was a massive shift in the car's acoustic profile. When the secondary barrels of a Holley or Rochester Quadrajet open up, the surface area for air intake effectively doubles. This creates a sudden change in the resonance of the intake manifold. For Marcus in 2026, hearing those secondaries kick in is a visceral confirmation of the engine's volumetric efficiency. It is a sound often described as a hollow wail or a deep-throated howl that originates from the center of the engine block and resonates through the hood. Step by step, we can analyze how the intake manifold acts as a resonator. The intake runners, the tubes that carry air from the plenum to the individual cylinders, have a specific length and diameter. These runners are tuned to a specific frequency, a phenomenon known as Helmholtz resonance. Just like blowing across the top of a glass bottle creates a specific note, the air vibrating inside the intake runners creates a standing wave. At a certain RPM, The frequency of the engine's intake valves opening matches the natural resonant frequency of the air in the runners. This results in an acoustic amplification. Potential outcomes of a perfectly tuned intake manifold include a significant boost in air pressure at the valve, which increases power, but it also creates a rhythmic, musical humming or drumming sound that can be heard even over the roar of the exhaust. In our 2026 case study, Marcus uses a variable-length intake manifold controlled by a modern ECU to maintain this resonance across the entire power band, creating a shifting, evolving intake note that sounds like a living, breathing entity. Then we must consider the raw, unfiltered sound of velocity stacks. Imagine a 1960s Trans Am race car, or a high-end 2026 custom build where the air cleaner has been completely removed in favor of individual polished aluminum trumpets sitting atop each intake port. This is the purest form of induction noise. Without an airbox to dampen the sound, you are hearing the actual pulses of the intake valve slamming shut. Every time a valve closes, a small shockwave travels back up the intake runner and exits the velocity stack. At 7,000 revolutions per minute, these thousands of tiny shockwaves merge into a terrifying metallic scream. This is a sound that historical trends suggest was the primary reason spectators at early road races could identify cars from miles away. It is a high-tension, high-frequency sound that feels much more mechanical and less muffled than a standard street car. As we move into the realm of forced induction, the acoustic landscape shifts dramatically. If Marcus decided to bolt a Root-style 6-71 supercharger onto his Chevelle, the intake sound would be dominated by the legendary blower whine. This sound is a combination of two distinct factors: the mechanical friction of the straight-cut timing gears and the compression of air between the rotating lobes. A Root supercharger is a positive displacement pump. It moves a specific volume of air with every revolution, regardless of pressure. As the lobes spin at twice the speed of the engine or more, they create a high-pitched siren-like wail. This is not just air movement. It is the sound of the air being physically beaten into the intake manifold. Data from acoustic mapping of high-boost superchargers shows that the whine can reach frequencies well above 10,000 Hz, which is why it is so piercing and can be heard from blocks away before the car even rounds the corner. In 2026, we see a divergence in these historical trends with the rise of centrifugal superchargers and turbochargers. A centrifugal supercharger sounds more like a jet turbine, with a high-pitched whistle that increases linearly with engine speed. This is caused by the impeller blades shearing through the air at supersonic speeds. A turbocharger, while also utilizing an impeller, has a more complex sound profile due to the wastegate and blow-off valve. When a turbocharger is under load, you hear the spooling, a rising whistle as the turbine accelerates. But the most iconic sound is the sneeze or chirp of the blow-off valve when the driver shifts gears. This is the sound of high-pressure air being vented to the atmosphere to prevent a pressure spike that could damage the compressor. While some enthusiasts in 2026 prefer the stealth of a quiet intake, others utilize open-at-atmospheric valves to maximize this mechanical drama. Case studies of the 1969 Pontiac GTO with the Ram Air Force system show how manufacturers tried to harness the sound and power of the intake by integrating it with the car's exterior design. By placing functional scoops on the hood, Pontiac engineers allowed the engine to draw in cooler, denser air from outside the engine bay. From an acoustic perspective, this moved the intake sound closer to the windshield. When the driver floored the accelerator, the sound of the intake was no longer trapped under a heavy steel hood. It was funneled directly toward the cabin. This created a much more immersive experience for the driver, making the car feel more alive. Imagine if Marcus in 2026 uses a similar cowl induction hood on his Chevelle. He would notice that at high speeds, the sound of the wind rushing over the car merges with the sucking sound of the intake, creating a unique aeroacoustic profile that is specific to that vehicle's shape. The density of the air also plays a critical role in the texture of the intake roar. On a cold, crisp morning in 2026, the air molecules are more tightly packed. This increases the Reynolds number, a dimensionless quantity used in fluid mechanics to predict flow patterns. Denser air creates more turbulence as it passes through the intake system, and turbulence creates noise. A car tuned for the thin air of the Rocky Mountains will sound subtly different than the same car running at sea level in Florida. The intake note at high altitudes is often described as thinner and less substantial, whereas at sea level, the engine sounds like it is literally tearing the air apart. This is another example of how the environment dictates the potential outcomes of automotive sound. As we have explored, the intake is far more than just a tube for air. It is a complex system of resonance, pressure differentials, and mechanical interaction. The sound of a 4-barrel carburetor opening up is a historical marker of American power, and the whine of a supercharger is a declaration of mechanical dominance. But these sounds are still external. They are what the car does to the world around it. To truly understand the legendary muscle car, we have to go deeper, under the valve covers and inside the crankcase. There is a whole other world of mechanical music being played by the camshaft, the lifters, and the timing chain. What does the metal-on-metal symphony of a high-performance valve train sound like when it is spinning at 8,000 revolutions per minute? We are about to peel back the layers of the engine block to hear the heartbeat of the beast next. To truly understand the heartbeat of a legendary muscle car, we must venture beneath the valve covers and into the very core of the engine block. While the exhaust provides the bass and the intake provides the tenor, the valve train is the percussion section of the automotive orchestra. Imagine it is a cool evening in October 2026, and an engine builder named Chloe is working in her shop in North Carolina. She is performing a final adjustment on a 1970 Chevrolet LT1 350 small block. In 2026, where digital precision is everything, Chloe still relies on a manual feeler gauge to set the valve lash. This engine utilizes solid lifters, a mechanical choice that defines its specific acoustic signature. Unlike hydraulic lifters, which use oil pressure to automatically take up any slack, solid lifters require a precise gap, measured in thousandths of an inch, between the rocker arm and the valve stem. This gap is the source of the legendary mechanical clatter, or sewing machine sound, associated with high-performance vintage engines. When the engine is running, the camshaft lobes strike the lifters, which push the push rods, which in turn pivot the rocker arms to open the valves. Because of that tiny gap or lash, there is a metallic click every time the parts make contact. At an idle of 800 revolutions per minute, you hear a rhythmic high-frequency ticking. But as Chloe brings the engine up to 3,000 revolutions per minute, those individual clicks merge into a continuous metallic whir. This sound is a historical marker of an engine designed for high RPM stability. Historical trends in the 1960s showed that solid lifters were the only way to prevent valve float at high speeds. And the potential outcomes of this engineering were engines that sounded like high-speed industrial machinery. The data suggests that a solid lifter valve train produces a frequency range between 2,000 and 5,000 Hz, a range that cuts through the lower frequencies of the exhaust and gives the engine an aggressive, high-strung personality. Step by step, the most influential component in this mechanical symphony is the camshaft. The camshaft is the brain of the engine, and its profile, the shape of its lobes, dictates not just how much power the engine makes, but how it sounds at rest. In 2026, Chloe is installing a cam with a high degree of overlap. Overlap is the period during which both the intake and exhaust valves are open at the same time. In a standard passenger car, overlap is minimized for a smooth idle. In a muscle car, high overlap is used to take advantage of exhaust scavenging at high speeds. However, at low RPM, high overlap causes exhaust gases to leak back into the intake manifold, diluting the fresh air-fuel mixture. This creates the iconic lopey or choppy idle. Imagine you are standing behind a 1969 Dodge Charger with a radical cam profile. The engine sounds like it is struggling to stay alive, with a rhythmic stumbling cadence. Thumper, thumper, thumper. This is not a sign of a poorly tuned engine. It is the sound of an engine that is optimized for the racetrack, essentially being choked at low speeds. Case studies of cam design, such as the famous Thumper series, show that engineers can specifically design low profiles to emphasize this sound without sacrificing too much street drivability. The potential outcomes of a high overlap cam include a dramatic drop in manifold vacuum, which you can actually hear as a deeper, more hollow resonance in the intake, and a sharper, more percussive hit in the exhaust note. Beneath the camshaft lies another mechanical sound source, the timing set. Most factory muscle cars used a silent timing chain with nylon-coated gears to keep the engine quiet for the average consumer. However, performance enthusiasts often swap these for double-roller chains or, more dramatically, gear drives. A gear drive replaces the chain with a series of straight-cut gears. Because the teeth are straight rather than helical, they create a significant amount of mechanical friction and noise. In Chloe's shop in 2026, she is installing a Pete Jackson-style gear drive into a custom build. The result is a high-pitched mechanical whine that sounds almost like a small supercharger. This whine is constant and rises in pitch with engine speed. Historical trends suggest that gear drives were popular not just for their timing precision, but for the intimidating acoustic presence they provided. It is a sound of pure mechanical intent, signaling that the engine has been heavily modified for durability in high-stress environments. As we go even deeper, we encounter the sounds of the reciprocating assembly, the crankshaft, connecting rods, and pistons. While these are usually muffled by the engine block and the oil in the pan, they contribute to the overall density of the engine's sound. In 2026, high-end builds often use forged pistons, which are designed to expand as they heat up. When a forged piston engine is cold, the pistons are slightly smaller than the cylinder bores, leading to a phenomenon known as piston slap. This is a subtle, hollow knocking sound that disappears once the engine reaches operating temperature. For an enthusiast like Chloe, piston slap is not a defect. It is a confirmation that the engine is built with high-strength components designed for extreme thermal expansion. The material of the valve covers also plays a massive role in the acoustics of the valve train. Imagine if Chloe replaces the stock stamped steel valve covers on her LT1 with thick, cast aluminum units. Stamped steel is thin and acts like a resonator, amplifying the ticking of the lifters and the splashing of the oil. Cast aluminum is much denser and provides significantly more sound dampening. The potential outcomes of switching to cast covers include a much quieter, more refined engine bay where the mechanical clatter is suppressed, allowing the observer to focus more on the induction and exhaust notes. Conversely, those seeking the raw, 1960s experience often stick with the thin steel covers to ensure the mechanical heartbeat of the engine is clearly audible. Furthermore, we must consider the cooling fan. In the era of legendary muscle cars, most vehicles utilized a belt-driven mechanical fan. As the engine revs up, the fan blades must move a massive volume of air to keep the radiator cool. This creates a powerful rushing sound, often described as a roar, that can actually mask the sound of the engine itself at high RPM. In 2026, many restomods use electric fans to save horsepower and clean up the acoustic profile, but the purists still love the sound of a mechanical fan engaging. It adds a layer of industrial heavy-duty texture to the car's sound, especially when the clutch fan locks up on a hot day, creating a massive vortex of air that you can feel standing 10 feet away. The symphony of the valve train is a reminder that a muscle car is a living, breathing machine made of thousands of moving parts, each with its own frequency and friction point. The clicking of the lifters, the whine of the gears, and the lope of the cam are the mechanical dialects of American power. But even the most perfectly built engine is only part of the story. Once that power leaves the crankshaft, it must travel through the drivetrain to reach the pavement. This journey introduces a whole new set of sounds: the howl of the transmission, the whine of the differential, and the scream of the tires. How does a Muncie 4-speed rock crusher transmission get its name? And why does a high-performance rear end whine like a jet engine? We are moving from the engine block to the gearbox to analyze the sounds of power transmission next. The transition of power from the crankshaft to the rear wheels is a mechanical journey fraught with friction, torque, and a very specific set of acoustic signatures that define the American muscle car experience. While the engine provides the voice, the drivetrain provides the resonance and the industrial backing track. Imagine it is the year 2026, and a restoration specialist named David is test driving a freshly rebuilt 1970 Chevrolet Chevelle SS. This particular car is equipped with the legendary Muncie M22 4-speed manual transmission. As David moves through the gears, the cabin is filled with a high-pitched, mechanical howl that rises in frequency with every mile per hour gained. This is not the sound of a failing component. It is the deliberate acoustic byproduct of the M22's engineering, famously known as the rock crusher. The reason for this specific name and sound lies in the geometry of the gears. Most standard manual transmissions of the era used helical cut gears. In a helical set, the teeth are cut at a steep angle, typically around 45 degrees. This allows the teeth to engage gradually, which results in a very quiet and smooth operation. However, the potential outcomes of this design include increased axial thrust, which can push the gears apart under extreme torque. To solve this for high-performance applications, Muncie engineers designed the M22 with much shallower angles on the gear teeth, roughly 20 degrees. These are often referred to as straight-cut gears, though they still possess a slight angle. Because the engagement is more direct and abrupt, the gears produce a significant amount of mechanical noise. Step by step, as the gears mesh at high speeds, the air and lubricant are squeezed out from between the teeth in a series of rapid pulses. These pulses create a constant, melodic whine that is the hallmark of a heavy-duty drivetrain. Historical trends show that while the average consumer found this noise intrusive, the muscle car enthusiast embraced it as a sonic badge of durability. In our 2026 scenario, David uses a chassis-mounted microphone to isolate the sound of the transmission. He notes that the whine is most prominent in first, second, and third gears. In fourth gear, which is a 1-to-1 ratio where the input and output shafts are locked together, the whine almost completely disappears. This change in the acoustic profile is a primary diagnostic tool for restorers. If the car whines in fourth gear, it indicates an issue with the bearings rather than the gear mesh itself. Case studies of the M22 reveal that the sound was so iconic that modern transmission manufacturers in 2026 often offer gear sets designed specifically to replicate that vintage howl, proving that the sound of power transmission is just as valuable as the power itself. Moving further down the line, we encounter the sounds of the automatic transmission, specifically the heavy-duty units like the Chrysler TorqueFlite 727 or the GM Turbo Hydromatic 400. Unlike the manual gearbox, the automatic transmission uses planetary gear sets. These systems create a different kind of whine, particularly in first gear. Imagine David shifts from the manual Chevelle into a 1969 Dodge Charger, equipped with a 727 TorqueFlite. As he pulls away from a stop, there is a distinct turbine-like whirring. This sound is caused by the sun gear and planet gears spinning within the ring gear. The potential outcomes of a high-stall torque converter also add to the soundscape. A high-stall converter allows the engine to rev higher before the car begins to move, creating a mismatch between the engine's roar and the car's physical velocity. This creates a sense of tension, where the engine is screaming at 3,000 revolutions per minute while the car is only rolling at 5 miles per hour. This acoustic tension is a defining characteristic of a built muscle car, signaling a drivetrain that is ready to launch with massive force. The journey of sound continues through the driveshaft and into the rear differential. The differential is where the direction of power is turned 90 degrees to reach the wheels, and this process is a major source of high-frequency noise. Most muscle cars utilize a ring and pinion gear set. In 2026, David is working on a Ford 9-inch rear end with 4.11 gears. A 4.11 ratio means the driveshaft spins 4.11 times for every 1 revolution of the wheels. This high gear ratio results in extremely high rotational speeds for the pinion gear. If the gear mesh is not shimmed to within 1/1000th of an inch of perfection, the result is a piercing whine that can be heard throughout the chassis. Historical trends in drag racing saw the use of even higher ratios, like 4.56 or 4.88, which produced a sound akin to a jet engine taking off. Step by step, the physics of this whine involve the contact pattern between the teeth. As the pinion gear drives the ring gear, the sliding action of the teeth creates friction. Under high load, the metal actually deflects slightly. In 2026, David uses a specialized acoustic camera to visualize the vibrations in the rear housing. He can see that the sound waves are being amplified by the large, hollow metal tubes of the axle housing, which act like the resonators of a musical instrument. To mitigate this, manufacturers often used heavy cast iron housings, but performance enthusiasts often switched to lighter, fabricated steel housings which, while stronger, tended to be much louder. This is a classic example of the trade-off between performance and acoustic refinement in the muscle car era. We must also consider the sounds of the tires and the suspension as they interact with the drivetrain. Imagine if David is performing a burnout in the 2026 Chevelle. The sound of the tires spinning is not just a squeal. It is a complex acoustic event. As the rubber reaches its glass transition temperature, it begins to vibrate against the pavement at high frequencies. This creates the classic high-pitched scream. Simultaneously, the suspension components are under extreme stress. In a car with leaf springs, you might hear the metallic clunk of the spring leaves rubbing against each other or the thud of the axle housing hitting the bump stops, a phenomenon known as wheel hop. This rhythmic thumping is a violent sound that signals a loss of traction and a mechanical struggle to put power to the ground. The potential outcomes of different tire compounds in 2026 also change the sound of the drive. A modern drag radial tire has a much softer, stickier compound than a vintage bias ply tire. When David launches a car on modern radials, the sound is more of a muffled chirp followed by a deep, low-frequency roar as the car grips and accelerates. The vintage bias ply tires, by contrast, would howl and scream for much longer, providing a more dramatic but less efficient acoustic display. This highlights how the evolution of materials has slowly changed the soundtrack of the American street. As the power finally reaches the pavement, we realize that the roar of America is a complete system. It starts with the air being sucked into the intake, moves through the combustion chamber, exits through the tuned headers, and is finally transmitted through a whining, howling drivetrain to the screaming tires. Every part of this machine is contributing its own frequency to the master recording. But there is one final element that ties it all together, something that turns a mechanical noise into a cultural icon. It is the environment in which these sounds are heard. The way a V8 sounds in an open field is completely different from how it sounds in an urban canyon or under a concrete overpass. We are about to analyze the acoustics of the American landscape and how the environment itself acts as the final amplifier for these legendary machines. What happens when the roar of a 454 big block hits the reflective surface of a highway tunnel? And why does that specific echo trigger such a powerful emotional response? We are heading out of the garage and onto the open road next. The open road is not just a path for travel. It is the final component of the muscle car's acoustic system, acting as a natural amplifier, resonator, and stage. Once the sound waves exit the tailpipes, they are no longer under the control of the engineer. They are at the mercy of the environment. To understand the true roar of America, we must analyze how these mechanical frequencies interact with the physical world. Imagine it is a clear, low-humidity evening in 2026, and a driver named Leo is piloting a restored 1971 Plymouth Hemi Cuda through the concrete canyons of downtown Chicago. In this year, where the city is increasingly populated by whisper-quiet autonomous shuttles, the entrance of a high-compression V8 is a seismic event. As Leo downshifts, the sound doesn't just dissipate. It strikes the vertical glass and steel surfaces of the surrounding skyscrapers and bounces back with redirected intensity. This is the urban canyon effect. Buildings act as massive reflective baffles, preventing the sound waves from spreading out and losing energy. Instead, the waves are funneled along the street level. Historically, city planners and acoustic engineers have noted that hard, non-porous surfaces like glass and polished stone have a reflection coefficient near 0.95, meaning 95% of the sound energy is reflected rather than absorbed. Step by step, when Leo's Hemi fires, the initial pressure wave hits a building and reflects within milliseconds. Because the distance between buildings is relatively short, these reflections happen so fast that our brains don't perceive them as distinct echoes, but as a massive increase in volume and sustain. This is known as reverberation. The potential outcomes of driving a muscle car in an urban environment include a perceived decibel increase of 6 to 10 decibels compared to an open field, effectively doubling the perceived loudness of the vehicle. The most dramatic manifestation of this environmental amplification occurs in the highway tunnel. Imagine Leo entering the Eisenhower Expressway tunnel. As he enters the enclosed space, the acoustic landscape shifts from a three-dimensional open field to a one-dimensional tube. In a tunnel, sound waves cannot escape upward or outward. They are forced to travel longitudinally down the length of the tunnel. This creates a phenomenon known as a standing wave. If the engine frequency matches the resonant frequency of the tunnel's cross-section, the sound can actually reinforce itself, creating a bone-shaking vibration that feels as if the entire structure is humming. Data from acoustic mapping suggests that the low-frequency thrum of a 426 Hemi, which centers around 60 to 80 Hz at idle, is particularly effective at exciting the air in concrete tunnels. For Leo in 2026, this is a sensory masterclass. Every throttle blip creates a wall of sound that travels ahead of the car, reaching the exit before the vehicle itself does. This is why the tunnel remains the ultimate proving ground for the American V8 roar. It is a space where the machine and the environment become a single vibrating instrument. However, the physics changes once Leo leaves the city and hits the open plains of the Midwest. In an open field, sound follows the inverse square law. This law states that for every doubling of the distance from the sound source, the sound pressure level drops by 6 decibels. In 2026, Leo notices that as he accelerates onto a rural two-lane highway, the sound of his car feels thinner. Without the reflections from buildings or tunnel walls, the high frequencies dissipate quickly, leaving only the low-frequency rumble to carry over the distance. Historical trends in long-distance sound travel show that low frequencies have longer wavelengths, which are less likely to be absorbed by the atmosphere or deflected by small obstacles like trees or road signs. This is why you can hear a muscle car approaching from miles away in the desert. You aren't hearing the mechanical clatter or the intake hiss, but the deep, subterranean bass of the exhaust pulses. We must also consider the role of atmospheric conditions, specifically humidity and temperature. On a hot, humid afternoon in 2026, the air is less dense because water vapor is lighter than dry air. Paradoxically, while the air is less dense, sound actually travels faster in humid air. Step by step, The increased presence of water molecules allows the sound waves to transmit energy more efficiently. Leo might notice that his CUDA sounds slightly sharper and more present on a humid day. Conversely, in the cold, dry air of a winter morning, sound waves are dampened more quickly. Temperature gradients also cause sound refraction. On a summer night, the ground cools faster than the air above it. This creates a temperature inversion where sound waves that would normally go upward are bent back down toward the earth. This is a primary reason why muscle cars seem much louder at night. The environment is literally trapping the sound and focusing it along the ground. One of the most iconic acoustic phenomena of the open road is the Doppler effect. Imagine a stationary observer standing by the side of the road in 2026, as Leo passes at 80 miles per hour. As the CUDA approaches, the sound waves are compressed in front of the vehicle, resulting in a higher perceived frequency or pitch. The moment Leo passes the observer, the waves are stretched out behind the car, causing the pitch to drop instantly. This creates the classic new sound. The mathematical formula for this shift involves the velocity of the sound source relative to the observer and the speed of sound in the current atmosphere. For a muscle car revving at 5,000 RPM, the frequency shift can be as much as a full musical fourth or fifth. This frequency drop is an auditory confirmation of velocity, a historical trend in automotive film and media, used to convey the sensation of speed to an audience. Case studies in road surface acoustics also reveal that the type of pavement Leo is driving on changes the car's roar. Asphalt is relatively porous and absorbs some of the higher frequency tire and exhaust noise. Concrete, especially the grooved concrete found on many U.S. interstates, is much more reflective and adds a high-pitched whirring or singing sound to the experience. In 2026, some specialized highways use quiet pavement technology designed to absorb decibels. But for an enthusiast like Leo, these surfaces can make the car feel disconnected. He prefers the raw, reflective nature of older asphalt, where the sound of the tires and the exhaust feels grounded and tactile. Even the presence of other vehicles in 2026 affects the sound. In a sea of streamlined aerodynamic electric cars, the blocky, upright profile of a 1971 Hemi CUDA creates massive air turbulence. At high speeds, this wind noise, the rushing and whistling of air over the chrome bumpers and around the A-pillars, merges with the mechanical roar. This is the aeroacoustic profile of the muscle car era. Unlike modern cars designed in wind tunnels for silence, these vintage machines were designed for style and presence. The sound of the wind fighting the car is a key part of the roar of America. It is the sound of resistance, of a machine forcing its way through the atmosphere by sheer mechanical will. As Leo drives into the sunset, the sound of his engine fading into the distance, we are left with a final realization. The environment is the canvas, but the engine is the brush. The way these sounds are captured and preserved is a science in itself. We have analyzed the machine, the fuel, and the road, but how do we accurately document this disappearing symphony for future generations? In an era of digital perfection, how do we record the raw, chaotic energy of a V8 without losing its soul? We are about to dive into the world of high-fidelity recording, microphone placement, and the art of capturing the legendary muscle car sound effects for the screen and beyond. We are moving from the road to the recording booth to master the art of the automotive soundtrack next. To master the art of the automotive soundtrack, we must transition from the perspective of the driver to the perspective of the audio engineer. In the year 2026, capturing the visceral energy of a 1969 Ford Mustang Boss 429 is no longer just about hitting a record button. It is a high-stakes exercise in managing extreme sound pressure levels and complex frequency overlaps. Imagine an audio archivist named Liam working at a specialized media facility in Los Angeles. His mission is to create a high-fidelity digital twin of the Boss 429's acoustic profile for a historical preservation project. In 2026, where the majority of vehicles on the road are electric, these high-resolution recordings are the only way future generations will experience the true texture of a high-displacement internal combustion engine. The primary challenge Liam faces is the sheer volume. A legendary muscle car at wide-open throttle can easily exceed 130 decibels at the tailpipe. This level of sound pressure is enough to physically damage the diaphragms of standard studio microphones. Step by step, Liam must select tools based on their maximum sound pressure level, or SPL rating. Historical trends in field recording favored dynamic microphones like the Sennheiser MD421 or the Electro Voice RE20. These microphones utilize a rugged diaphragm and a voice coil that can handle massive air movement without clipping or distorting. In 2026, Liam utilizes a modern evolution of these designs, featuring carbon fiber diaphragms that can withstand the violent pulses of a 429 cubic inch engine, without losing the nuance of the high-frequency mechanical clatter. Placement is the most critical variable in the recording process. To capture the full spectrum, Liam employs a multi-mic array. First, he addresses the exhaust. A common mistake in amateur recordings is placing the microphone directly in the path of the exhaust gases. This results in wind buffeting, where the physical force of the air hitting the diaphragm creates a low-frequency distortion that masks the actual sound of the engine. Liam places a high SPL dynamic microphone, approximately 2 feet away from the tailpipe, angled at 45 degrees off-axis. This position captures the pressure waves of the exhaust pulses, while allowing the actual gas to pass by the microphone safely. Potential outcomes of this off-axis placement include a much clearer representation of the individual combustion events, allowing the listener to hear the distinct pop and crackle of the overrun. Simultaneously, Liam must capture the engine bay. This is where the mechanical heart of the car resides. He uses a pair of small diaphragm condenser microphones shielded by high-temperature windsocks. These are placed near the intake and the valve covers. The goal here is to capture the high-frequency details, the whistling of the carburetor venturis, the clicking of the solid lifters, and the whine of the alternator belt. These sounds are often lost in exterior recordings, but they are essential for creating a realistic sense of presence. Data from acoustic modeling suggests that these high-frequency components, ranging from 5,000 to 15,000 Hz, are what the human brain uses to identify the proximity and scale of a mechanical object. Without them, the recording sounds like a generic rumble. With them, it sounds like a living machine. Imagine if Liam were to use a binaural recording setup inside the cabin. Binaural audio uses 2 microphones placed inside a dummy head or clipped to the ears of a human operator to mimic the way human ears receive sound. In our 2026 case study, Liam sits in the passenger seat of the Boss 429 as it performs a high-speed run on a closed course. The binaural microphones capture the sound as it reflects off the dashboard, the vinyl seats, and the glass windows. This creates a 3-dimensional soundstage where the listener can actually perceive the direction of the engine's roar relative to the interior space. Historical trends in high-end automotive cinema have increasingly relied on this technique to provide the audience with a more immersive, first-person experience. The recording hardware itself has evolved significantly by 2026. Liam utilizes a field recorder capable of 32-bit float recording. This is a crucial technical detail for muscle cars because of their incredible dynamic range. A V8 can go from a relatively quiet 70 decibel idle to a deafening 140 decibel scream in a matter of seconds. In traditional 24-bit recording, if the gain is set too high, the loud peaks will clip and be lost forever. If the gain is set too low, the quiet details are buried in digital noise. 32-bit float technology essentially eliminates the need for gain adjustment by providing a dynamic range so vast that it can capture both the whisper of the cooling fan and the roar of the exhaust with perfect clarity in the same file. This allows Liam to preserve the raw, uncompressed energy of the car, providing the potential outcomes of a truly lifelike reproduction. Case studies in sound design for the gaming industry often highlight the use of contact microphones. These are microphones that do not pick up air vibrations, but instead sense the vibrations of the solid objects they are attached to. Liam attaches contact mics to the engine block, the transmission housing, and the rear differential. These tracks provide a low-frequency, tactile layer to the final mix. When combined with the airborne recordings, these contact tracks add a sense of weight and physical impact. You don't just hear the gear shift. You feel the mechanical thud of the internal components engaging. This layering technique is the secret behind the most iconic car sounds in modern media. It bridges the gap between a simple audio recording and a sensory experience. Another critical step-by-step process is the management of environmental noise. Even at a private track in 2026, there is ambient sound, wind, birds, and distant city traffic. To isolate the muscle car, Liam uses highly directional shotgun microphones for the pass-by shots. These microphones have a narrow pickup pattern that rejects sound from the sides and rear, focusing solely on the vehicle as it approaches and recedes. This allows him to capture a clean Doppler shift without the interference of the surrounding environment. He also uses specialized software to analyze the frequency spectrum and remove unwanted persistent noises, such as the hum of the electrical grid or the sound of the wind through nearby trees, ensuring that the final archive is a pure representation of the machine. As Liam finishes his recording session, he has captured over 20 channels of synchronized audio. He has the raw intake growl, the mechanical clatter of the valve train, the howling of the drivetrain, and the thunder of the exhaust, all mapped to the RPM and throttle position of the vehicle. This data is then used to create a digital sound model. But even the most perfect recording is only as good as the context in which it is used. The Roar of America is not just about the machine. It is about the legacy and the emotional resonance it carries. We have spent 9 parts dissecting the physics, the chemistry, and the technology of these legendary sounds. Now we must bring it all together. We are entering the final stage of our masterclass. We have looked at the past, analyzed the present of 2026, and documented the mechanics. Now we must look at the future of the American roar. As we move into the final part of this series, we will examine the cultural impact of these sounds and the emerging technologies trying to replicate them in an electric world. Can a digital synthesizer ever truly replace the soul of a 426 Hemi? We are looking at the legacy and the final frontier of muscle car sound effects next. The silence of 2026 is a striking departure from the heavy mechanical atmosphere of the previous century. As we stand at the edge of this new era, the question of legacy becomes paramount. For a young driver named Elena, navigating the streets of a major American city today usually involves the near-silent glide of an electric powertrain. However, Elena is part of a growing movement of enthusiasts dedicated to the preservation of the internal combustion soundtrack. She owns a 2026 electric performance coupe that features one of the most advanced sound synthesis systems ever developed, a technology often referred to as active sound enhancement or external sound generation. This system attempts to bridge the gap between the silent future and the thunderous past. But can a digital array of speakers and transducers truly capture the essence of a 1974 126 Hemi? To answer this, we must look at the final frontier of muscle car sound, the intersection of digital replication and organic physics. Case studies of modern automotive sound design in 2026 highlight the development of systems like the Fretsonic chambered exhaust. This is not merely a speaker in a tailpipe. It is a complex acoustic chamber designed to move air in a way that mimics the back pressure and resonance of a traditional exhaust system. The potential outcomes of this technology are fascinating. By using a transducer to vibrate a series of internal baffles, manufacturers can produce sound levels exceeding 120 decibels. For Elena, when she engages the high-performance mode in her car, the exterior speakers emit a low-frequency growl that shifts in pitch and intensity based on her throttle input. This is achieved through real-time waveform synthesis, where a digital signal processor calculates the exact harmonic profile of a V8 engine thousands of times per second. Step by step, the synthesis process begins with a lookup table of recorded engine notes, many of which were captured using the exact techniques Liam utilized in our previous recording masterclass. These recordings are sliced into granular fragments and reassembled based on the motor's current RPM, load, and temperature. However, data from high-fidelity acoustic testing reveals a phenomenon known as the uncanny valley of automotive sound. Just as a digital human face can look almost real but feel slightly off, a synthetic V8 sound often lacks the chaotic, non-linear variables of a mechanical engine. Historical trends in sound synthesis show that while we can replicate the primary frequencies of a 454 big block, it is much harder to replicate the random misfires, the subtle mechanical friction of a dry timing chain, or the unique way a cold engine stumbles before it reaches operating temperature. Elena notices this difference when she parks her modern coupe next to her grandfather's vintage 1970 Plymouth. When the old Hemi starts, the sound is not just an audio event, it is a physical one. The air around the car is physically displaced in violent pulses. These pulses create infrasound frequencies below 20 Hz that the human body feels as a vibration in the chest and stomach. This is the tactile component of the roar. Synthetic systems in 2026 are beginning to address this by using haptic transducers built into the chassis and the seats, vibrating the car to simulate the lope of a high-lift camshaft. While these potential outcomes provide a more immersive experience for the driver, they still struggle to project that same physical pressure to a bystander 10 feet away. The organic roar of a muscle car is a three-dimensional wave of moving mass, whereas the synthetic roar is a two-dimensional projection of sound. The psychoacoustic impact of these sounds on the American public is rooted in evolutionary biology. Research suggests that the low-frequency, high-amplitude sound of a large engine triggers a specific neural pathway associated with large predators. This leads to a spike in adrenaline and a heightened state of awareness. Historical trends in automotive marketing in the United States capitalized on this biological response for decades, branding the V8 roar as a symbol of power and freedom. In 2026, as we transition away from these engines, many experts are concerned about the loss of this sensory heritage. This is why projects like the Global Engine Sound Archive have become so vital. These archives use the 32-bit float recordings we discussed to ensure that the exact frequency maps of every legendary muscle car are preserved with forensic accuracy. Imagine if, in the year 2050, a student could put on a pair of high-fidelity headphones and experience a 100% accurate recreation of a 1969 GTO through a highway tunnel. The science we have covered in this masterclass, from the flame front velocity of the fuel to the reflection coefficients of the concrete walls, provides the metadata for these future simulations. We are documenting the soul of the machine so that it can be digitally resurrected. The data points we collect today, such as the specific 154263778 firing order of a Ford small block, are the DNA of the American roar. By understanding the physics of the exhaust pulse and the resonance of the intake manifold, we ensure that the legendary muscle car remains a living part of our cultural memory, even if the fuel that once powered it becomes a relic of the past. The final element of the legacy is the human element. For enthusiasts like Elena, the sound of a muscle car is a bridge across generations. It is a connection to a time when engineering was visible and audible. When she hears the rhythmic thumping of a vintage V8, she isn't just hearing a machine. She is hearing the story of American industrial might, of late-night garage builds, and of the open road as a symbol of infinite possibility. The potential outcomes of our current technological shift mean that we may soon live in a world of silent efficiency, but the echo of the muscle car era will continue to vibrate through our media, our movies, and our memories. As Elena drives her silent coupe back home in the twilight of 2026, she occasionally switches off the synthetic sound system just to appreciate the quiet. But every once in a while, when the road is empty and the moon is high, she reaches for the dial and brings the roar back to life. It is a digital ghost of a mechanical titan, a reminder of the power that once defined the American highway. We have explored the big three signatures: the chemistry of high-octane combustion, the physics of the exhaust, and the art of the recording. This has been a deep dive into the very fabric of automotive sound. The roar of America is a symphony of steel and fire that took nearly a century to compose, and though the instruments are changing, the music remains. We have reached the end of this mechanical deep dive, having stripped the muscle car down to its last acoustic vibrating part. But the world of automotive sound is vast, and the American V8 is only one chapter in a much larger global story. What happens when we leave the torque-heavy highways of Detroit and head to the high-revving mountain passes of Japan? How does the scream of a twin-turbocharged inline-six or the high-pitched wail of a rotary engine challenge the dominance of the V8? We are preparing to cross the Pacific to analyze the high-frequency engineering of the JDM legends and the science of the turbospool next. Would you like me to begin the script for the next masterclass series? The Scream of the East, JDM sound engineering and turbocharged harmonics?